Hello everybody. In this video I'm going to get into some of the quantitative math for pH acids and bases, including Kw, pH, and pOH. But the first thing I want to do is a little bit of review of some math that you may or may not already be familiar with, called the log rules. So a log is a function, and if I have the log of a times b, that's going to be equal to the log of a plus the log of b. If I have the log of a divided by b, I get the log of a minus the log of b. And if I have the log of a raised to the b power, that is going to equal b times the log of a. I want to note that when we write a log like this and we do not specify what the base is, we're going to assume that to be a base of 10, which means that to invert this equation and figure out what x is going to equal 10 raised to the power of y. And this gives you some sense of what the log is. It's the inverse of this function right here. Now, the question you might ask is, why do we even care about logs? Logs really do a number of things. They kind of pop up naturally in science a lot, but mostly because we can use all of these different properties of logs in order to manipulate equations. The other thing that it does is it helps us to work with reasonable numbers when we have really large scales, really big numbers and really small numbers. It can be convenient to look at them as logs. So the first thing that we're going to look at as we're trying to quantify acid-base equilibriums is the autodissociation of water in water. And what that means is that water will naturally break down into free hydroxide ions and free protons all on its own. There's this equilibrium here. There's not a lot of them that do this, but some portion of them are going to just break down in any water sample, a pure water sample. If we write down our equilibrium constant for this, we're going to note that it is the one for water here with this W. We wind up with something that looks like this, but we know that water is a pure liquid and we're not going to include it. That goes to 1, and we get this product of the concentration of hydroxide ions times the concentration of proton ions at equilibrium here. And when we are at 25 degrees Celsius, because we know that equilibrium constants are sensitive to temperature, we know what this value is. It is 1 times 10 to the negative 14th, a really small number, indicating that there really isn't very many of these at all that are being converted over from the water. Now, if I take the log of both sides, I get the log of Kw, and so here I have the log of Kw, and I get the log of this product here. Using my log rules, I can say that that is equal to the log of the hydroxide ion concentration plus the log of the proton ion concentration. And then I can go through and multiply them all by -1. So I multiply both sides by -1. I get the negative log of Kw is equal to the negative log of the hydroxide ion concentration plus the negative log of the proton concentration. Now, why did I do that? I did that because these all have specific definitions. The negative log of Kw is something we call pKw. The negative log of the hydroxide ion concentration is pOH, and the negative log of the proton concentration is pH. Why specifically do we do the negative log? Well, if I take the log of this number here, remember that the answer to a log is an exponent, I'm going to get -14. But I want to work in positive values. So I want my pKw to be positive, so I make it the negative log. And I work that out for us here. pKw is equal to the negative log of 1 times 10 to the negative 14, which is equal to 14. And so our conclusion is that pOH plus pH is equal to 14. And this value here is where we get the sense that, this kind of misnomer that the pH scale is going to run between 0 and 14, with 7 being a neutral solution. While it is very true that 7 is a neutral solution, because remember this is the concentration of H+, so when we have equal numbers of these two and it equals 10 to the negative 14, I'm going to wind up with a pOH of 7 and a pH of 7. It is not true that the bottom of this scale is equal to 0 or that the top of this scale is equal to 14. And I'm going to show you some examples to prove that in a little bit. So from that bit of math that we just did, we wind up with some important conclusions here that allow us to convert between various values that we're going to be dealing with here. And these are going to be very important for you to finish your homework. So you should note them down as you're watching this video. First, converting from the concentration of proton atoms to the concentration of proton atoms from pH, we're going to do 10 to the negative pH is going to give us the concentration of protons. If we want pH, but we have the concentration of protons, we'll take the negative log of that value, and we get our pH. We can do the exact same thing with the concentration of hydroxide ions and pOH to interconvert between those. And when we want to convert from pH to pOH, we do 14 minus the pOH is going to be the pH, and the pOH is going to be 14 minus the pH. And finally, if we want to convert between the concentration of proton ions and the concentration of hydroxide ions, well, we know that Kw is equal to this product. So the concentration of hydroxide ions is going to be Kw divided by the proton concentration, or 10 to the negative 14 divided by the proton concentration, because that's what Kw is. And our concentration of protons is going to be Kw divided by the concentration of hydroxide ions, which is 10 to the negative 14 divided by the concentration of hydroxide ions. So let's take a moment here to see what we can interpret from pH and pOH. When pH is less than 7, the concentration of protons is in excess, so there's more protons than hydroxide ions, and the solution is acidic. When the pH is greater than 7, the hydroxide ions are in excess, and the solution is basic. The reverse is true for pOH. When it's less than 7, this means that the solution is basic, and when it's greater than 7, it means that the solution is acidic. And it's important for you to understand that a difference of 1 pH unit is 10 times the difference in concentration. So because it's now a logarithmic scale, it's no longer linear, and every single time we move a pH unit, we're actually getting 10 times the more concentration. So for instance, a pH of 3 would correspond to a hydrogen or proton concentration of 10 to the negative 3, or 0.001 molar. pH of 2 is going to be 0.01 molar, 10 times more concentrated, and a pH of 1 is going to be 0.1 molar. Let's take a look at an example here. What is the pH of a 3 molar HCl solution? So we know that pH is equal to the negative log of the hydrogen ion concentration. We'll assume, because this is a strong acid, that it completely dissociates. We'll take the negative log of 3 molar. Remember that these concentrations, whenever we're working, should be in molarity. And we get a value of negative 0.5. This shows that it is not true that the pH is limited to values between 0 and 14. It could actually even go lower than this. The most concentrated solution that you can make out of hydrochloric acid is 12 molar, so 4 times more concentrated. The pH of a solution is measured and found to be 4. What is the hydrogen ion concentration, and what is the hydroxide ion concentration? So the first thing we'll do is we'll convert that pH that we're given to the concentration of hydrogen protons here. So we have 10 to the negative pH, 10 to the negative 4 is 0.0001 molar. And then we can convert this value to the concentration of hydroxide ions by using this formula, Kw divided by the value we just calculated, 10 to the negative 14 divided by 10 to the 4, and we get 10 to the negative 10 molar, or 1 times 10 to the negative 10 molar. We could have alternatively converted the pH value we were originally given of 4 to pOH. 14 minus that pH would have been 14 minus 4. That would have gave us 10. And then we could have converted that to the concentration of HO minus, just like we did here. 10 to the negative pH is 10 to the negative 10 molar, and you can see that we would have gotten the exact same answer. So a lot of these questions are basically going to do that. They're going to give us a bit of information and then kind of make us go through different steps to get to it. So they're not going to give us the information that's convenient to calculate directly the thing that we want to know. But we've seen these problems so far, and you guys have been doing really great on them. So I think that you'll do just fine. Do remember that you can get a little confused with some of these problems because, like we've seen, there's more than one way to do it. So don't let that confuse you. Just pick a way that you like and kind of, stick with it.